Hello everyone, my name is Keisuke FUJII from Osaka University, and first of all, I'd like to thank all organizers and attendee for providing me this nice opportunity. So today, I'd like to talk about the general introduction to fault-tolerant quantum computing. That is a goal of this Moonshot program in 2050. So let me start with why quantum error correction from the beginning. So, quantum information is encoded into the superposition of the two quantum states, superposed state of the 0 state and 1 state. This quantum nature of the information is very important for quantum computer to be more powerful than the classical counterpart. But the superposed state is very fragile. So if you see the state is whether 0 state or 1 state, easily the quantum state is destroyed and becomes classical information, either 0 or 1 state. Of course, we do not measure the quantum state during the computation, but unfortunately, undesirable interaction with environment between the environment and the quantum bit causes some decoherence, destruction of the quantum coherence. So the quantum information is easily destroyed. And you know, if the number of quantum bit is increased, the number of the complex amplitude, which describes the complex quantum state, increase exponentially. And also these exponentially many amplitudes are suffering from the analog noise. And also, unfortunately, in the quantum world, there is no cloning theorem. So the unknown quantum state cannot be copied. So in that sense, in the early stage of the quantum computing, quantum computer is thought to be the analog computer, and protecting the quantum information against analog noise was thought to be difficult. So here is a very famous footnote argument by the Landauer. So all papers on quantum computing should carry a footnote. This proposal, like all proposals for quantum computing, relies on speculative technology, does not in its current form take into account all possible sources of noise, unreliability, manufacturing error, and probably will not work. So, but nice thing is actually Peter Shor showed that actually quantum information can be protected against analog noise. So let me briefly explain about how quantum error correction works. So basically, the quantum information plotted on the troposphere is actually affected by the interaction between the environment. So this can be regarded as a kind of entanglement between the qubit of interest and the surrounding environment. And in order to tackle this entanglement between environment, we can also use the entanglement with multiple qubits. So the idea of quantum error correction is here. So here we have a very simple quantum error correction code using the 3 quantum bits. So actually quantum information is encoded into the subspace of the entangled multiple qubits. The logical 0 state is described by 000 state, and logical 1 state is represented by the 111 state. And then suppose individual qubit is affected by some analog noise, like here, but still we can do the measurement on what digital error occurs on the logical qubit. So in this way. So more precisely, if we do some parity check measurements between the neighboring qubits, then we we obtained the parity is odd here, and again odd here, odd here. So in this way, by doing the parity projection on the logical degree of freedom, the analog error can be decomposed into the digital error, whether the error is occurred or not occurred. So in this way, in short, quantum error collection embeds quantum information into the entangled multi-qubit system so that analog noise can collapse these into the digital errors. So what is fault tolerance? Basically, in order to achieve fault tolerance, we have to do more. So here is a kind of approach of fault-tolerant quantum computing based on the concatenated quantum computing. So starting from the physical gate operation here, we encode quantum information into the quantum error collection code, which I previously explained. And then, just after the logical gate operation, we perform quantum error collection so that the erroneous state is recovered to the original quantum state. And this quantum error correction circuit is appropriately designed. Then if any single point of error can be collected during this error collection procedure, then the logical error probability is decreased to the p to the square. P is the physical error probability. And by repeating this encoding map recursively, or we can also say this as a concatenated quantum computing, then the logical error probability is decreased further by further by increasing the concatenation level. And then, if the physical error probability is smaller than the certain threshold value, then we can decrease the logical error probability super exponentially in the concatenation level. So this is the so-called threshold theorem. And this threshold value is the very important target for the experimentalist to achieve fault tolerance. So here, I will show the history of the threshold value. So in the beginning of the fault-tolerant quantum computing, actually the threshold value is very small, something like 10 to the minus 6 here. But the fault-tolerant scheme has been improved further by further, and the threshold value is improved. For example, in 2005, Emmanuel New proposed the post-selected fault-tolerant quantum computing, whose threshold value is around 1%. But all these proposals are based on the concatenated quantum computing, and most concatenated quantum computing require almost all-to-all qubit gate operation, which means that it's very difficult to implement on the 2D nearest neighbor architecture. And if we map these concatenated quantum computing on the nearest neighbor to the architecture, the threshold value was thought to be become very small, like 10 to the minus 5. But soon later, Robert Rausendorf proposed the very nice fault-tolerant quantum computing, which approaches the threshold value around 1% with only using the nearest neighbor 2-qubit gates on the 2-dimensional array of the qubits. So actually, this is another direction for the achieving the fault-tolerant quantum computing using the quantum error correction code, so-called surface code. So let me briefly explain about the surface code. So here the circle represents the qubit, which is aligned on the square lattice. And the gray circle corresponds to the data qubits on which the quantum information is encoded. And then the white circle correspond to the measurement qubits to do the parity check, which is so-called syndrome measurements. So by using this measurement qubit, syndrome qubit, we can measure the parity of the neighboring 4 qubits by using the 2-qubit gate on the nearest neighbor 2 qubits. And then we perform this syndrome measurement repeatedly, and then errors are detected during this syndrome measurement, and the location of error is estimated to perform some recovery operation. And if we think about fault-tolerant quantum computing, we have to take all sources of error, namely the state preparation error, measurement error, gate operation error, and also idling error. So if the qubit is waiting for the next operation, qubits would decohere due to some T1 or T2 realization. So and if we take all these imperfections into account, we can estimate the threshold value below which we can perform quantum error correction. And then the threshold value is something like 1%. So in other words, if we can achieve 99% state preparation, measurement, gate operation, then we can definitely demonstrate the quantum error correction to protect quantum information from error. And this level of the fidelity, ultra high fidelity, is actually achieved in 2014. So John Martinez's group in UCSB reported this superconducting quantum circuit at the surface code threshold for fault tolerance, and they achieve pretty ultra high fidelity quantum gate operation, single qubit gate 99.92%, 2-qubit gate 99.4%, and measurement 99%. So actually, while these qubits are aligned online, not 2-dimensional array, and the number of qubits is still very small. At that time, it's only 5 qubits, but this ultra high fidelity result is enough for Google to understand actually constructing fault-tolerant quantum computer is not impossible. So in 2014, Google decided to enter the quantum computing race. So the important thing here is actually, at that time, there is no terminology NISQ. So actually, Google entered this field for quantum computing because of this fact. So they believe that actually the large-scale fault-tolerant quantum computing is actually possible. And then, since then, actually, we almost experienced 10 years since then. And I think this year, 2023, is the first year of the practical quantum error collection. So in recent years, we observed very exciting quantum error collection experiments. Specifically, the last year, the 3 different groups reported the quantum error collection demonstration using the surface code, 17-qubit surface code from Zurich, I guess, and from China. And more recently, the Google reported 49-qubit surface code quantum error correction demonstration. And they demonstrate that actually if the size of quantum error correction code is increased, then the logical error rate is decreased. So the amount of the logical error rate decrease is very small, but this fact indicates that actually we are in we are actually below the threshold, just below the threshold. And if the error probability is further suppressed, and if the size of the quantum error correction code is further increased, then the logical error rate is exponentially suppressed. So hopefully this year or in the near future, we can observe that quantum error correction can extend the lifetime of the logical information longer than the physical qubit lifetime. And we want to see the whole picture of the fault-tolerant quantum computing. So here is a qubit, and here is surface code, and there is a very important metric of the error correction code called code distance D. So actually, roughly speaking, the code distance D means that how much amount of error can be collected. Half of the D errors can be collected by using the error correction code with code distance D. And then for the surface code, in order to construct the code distance D error correction code, we need 2D squared minus 1 physical number of qubits. And then the logical error rate is decreased in this way. Here is P is the physical error probability, and P threshold is the threshold value. And the exponent of the logical error probability is determined by the code distance, D plus 1 divided by 2. So to be concrete, for example, if the physical error probability is the 10 to the minus 3, and the threshold value is 1%, and if we choose the code distance 19, then roughly speaking, the logical error probability can be suppressed to the 10 to the minus 10. And in this case, we need 721 physical qubits per single logical qubit. And by collecting these logical qubits, we can construct whole fault-tolerant quantum computing architecture. And depending on the algorithm which we want to implement, basically we need from 100 to 1,000 logical qubits to do some interesting quantum algorithms. So in total, we definitely need the physical qubits, something like 10 to the 6. 1 million qubits would be required. And then, so here is a possible configuration of the surface code quantum computing with lattice surgery. So these black square indicate the data logical qubit on which some logical data of quantum computation is located. And these gray squares are employed for some logical operation in between the logical data qubits in this way, which is so-called lattice surgery technique. But unfortunately, the logical operation which can be easily implemented on this architecture is very limited to the Clifford gates operation. So basically, there is two kinds of logical operation. One is the Clifford gates, and another is non-Clifford gates. The example of the Clifford gate is Pauli X, Y, Z, Adamo, S, C, control Z, and some other thing. Basically, these gates are very simple. The state which can be generated by using the Clifford gate is very limited on the Hilbert space. So in that sense, we can fully simulate the quantum state which can be generated by the Clifford state, which is well known, the Gottesman's-Niels theorem. On the other hand, if we are allowed to use the non-Clifford gates like T gate or Toffoli gate, then we can fully expand the Hilbert space. So in that sense, the quantum computation generated by Clifford and non-Clifford gates can generate quantum states dense in the Hilbert space. So we can implement an arbitrary quantum computation with combining Clifford and non-Clifford gate. But unfortunately, this non-Clifford gates is very difficult. These gates are very difficult to be protected against noise. So in order to protect the non-free fault gate, we need some additional care, which is called magic state distillation, where the special, the unsure state, so-called magic state, is distilled. And then the clean magic state is supplied to implement the non-free fault gate by using the gate teleportation. So finally, we would like to see the layered structure of the fault-tolerant quantum computing, starting physical layer. So the hardware layers, there are still a lot of candidates for the fault-tolerant quantum computer. Starting from the superconducting qubit, trap-and ion, semiconductor qubit, photonic qubit, and neutral atom qubits. Depending on the individual physical system, you have to design how we can control each individual system and how we can achieve high fidelity gate operation. And then by using these gate operation, we have to perform some error detection, syndrome measurements for error collection, and then we have to perform some error collection depending using the information obtained from the syndrome measurements. And actually the estimation of the location of the error from the syndrome is very complicated, something like the game Minesweeper or something. And we have to perform some syndrome measurement very fast within the coherence time of the qubit. So it's very challenging to decode the errors within realistic time for the feedback operation for the quantum error collection. So nowadays, real-time decoding attracts much attention for implementation of the quantum error collection. So this kind of topic is one of the target for the Moonshot program led by the Kobayashi PM. And then after the quantum error collection, we can perform fault-tolerant logical gate operation by the lattice surgery or defect blading and so on. And as I said, in order to achieve universal quantum computation, we need additional care, magic state distillation for the non-Clifford operation. And after that, above this layer, we can see the quantum computer as a digital quantum computer, where the accuracy of each logical operation is guaranteed. And then, in order to implement quantum algorithm, we have to decompose and compile and optimize the quantum algorithm into the elementary logical operation. And then finally, we can perform the quantum algorithms, factoring, machine learning, quantum chemistry, condensed matter physics, and so on. So let me see some resource estimates for solving some classically intractable problems. So the first example is prime factorization. If we want to factor 2,000 bits, then we need 20 million qubits, and it takes 8 hours for factoring. And for the quantum chemistry, the target here is actually the FEMOCO, which is related to the nitrogen fixation. In this case, the number of qubits is 2 million qubits, and it takes 2 weeks to get the result. And very recently, the group of the Quash professors Moonshot program reported that much smaller number of qubits is enough to demonstrate some advantage in the field of condensed matter physics, such as the Heisenberg model or Fermi-Hubbard model. There, the number of qubits is required is smaller than 1 million qubits, half of the million qubits, and 15 hours to get the outcome. Where some sophisticated compilation and the quantum algorithms like the block encoding and phase estimation is employed. So finally, I would like to share one more thing about the early FTQC. So nowadays, the quantum computing device is still in the NISQ era. So, there is a quantum chasm, a large gap between the NISQ and the FTQC. The state-of-the-art quantum computer can perform some tasks that are interactable for classical computer, such as the random quantum circuit sample demonstrated by Google. But still, quantum advantage in meaningful tasks is missing. So if the demonstration is shallow quantum circuit, then it would be possible to achieve some quantum advantage, but the shallow quantum circuit is also easy for classical computer to counteract. So in that sense, here is a natural question. Can we achieve some quantum volume advantage? The quantum volume is a metric of the performance of a quantum computer using the relatively deeper quantum circuit. And the current quantum computing devices are reaching the over 100 qubit, but still the quantum volume is very limited. And if your quantum computer is the 2D square lattice architecture, the quantum volume we can achieve is very limited. So even if the error probability is 10 to the minus 4, the theoretically achievable quantum volume is 37 qubits, which is still classically simulatable by using a high-performance computer. On the other hand, as we saw, the fully fledged quantum computer required 1 million qubits. So in this sense, there is a large gap between the NISQ, meaningfully employed number of qubits, and the FTQC, required number of qubits. So to close this gap, we recently reported partially fault-tolerant quantum computing architecture. Because time is limited, I briefly explained. So the assumption is 10,000 qubits, and the error rate is 10 to the minus 4. Our idea here is actually we skip magic state distillation for non-Clifford gate operation, but we carefully inject some special unsure states for the non-Clifford gate operation. So that we can achieve the quantum volume of the 2 to the 64 with 10,000 qubits and 10 to the minus 4 error rate. So this can be the milestone, intermediate milestone between the NISQ and FTQC. So this is the final slide, and the time is running. So I would like to finish my talk. Thank you for attention.